Hey, BC Calculus. So this is the fourth lesson. This is what we would do on day 3 normally, and it's looking at two different things. It's looking at when do you have limits that are infinite, and how do you say that, and what happens when you look at limits at infinity, meaning we're looking infinitely far in the x direction. Basically, we're talking about infinity up and down, and then infinity left and right. So we start off with these functions, and so now you can, on a limit question, you can answer a number, infinity, negative infinity, or you can say the limit does not exist. Those are your options, right? So for each of these functions, we want you to identify any vertical asymptotes that there are, and do a very rough sketch. This is just like a quick one, just for your notes. It's not, graded or anything like that. What did it look like? And do it on your calculator. So if you remember how to graph this, great. But still, do it on your calculator, on your handy dandy calculator, so that you can go over doing that. If any of you have calculator issues, we're going to definitely spend some time in class helping you out with that. So graph them and then figure out what are the vertical asymptotes, and then are there any removable discontinuities? That's where you've got a little space in the graph. So it's a discontinuity because there's no value there. Yeah, we could say that. There's no value there, but it's just there's no value for a moment, but then it keeps going with whatever it was doing. Okay? And then try to figure out what the limits would be from the left, from the right, and then overall. So try each one of these, graph them. I'm going to do the same, and then find all the limits. So I'm going to pause it and put the answers in. I should give you a moment to pause it. Okay, that's enough time. Okay, we're mostly done. We ran into some technical issues. I have the problem when I make a table and try to write on it on the Surface Pen, the writing migrates. You probably have the same issue sometimes. I looked in a bunch of forums, and there's a lot of people who've complained about this. That's all I know. Okay, so I don't see an answer anywhere. All right, so what's going on? All right, so some of the answers I tried to write, and it just kept migrating, and I got too frustrated. So we'll just go through it another way. First one, the graph looks like that. There's a vertical asymptote at x equals 3, and there are no removable asymptotes, and there are the limits. It's getting closer to negative infinity on one side and negative infinity on the other side. And so the limit overall is negative infinity. Works great. For the second one, there's a vertical asymptote at x equals 4. But the interesting thing is, as you're approaching one way, it's approaching from the left, it's going to negative infinity. As you're approaching from the right, it's going to positive infinity. So if you try to ask the limit question in general, I'll write this and it'll probably migrate. Yeah, figures much. Then, can I do that? Yeah, there we go. Then the answer is it does not exist. So this one right here, the limit as x approaches 4 of this. Oh, I'm not responding. Okay, I'm going to keep talking though. The limit as x approaches 4 overall doesn't exist because you don't have an answer. Because on one side it has one answer, on the other side is a different answer. So you don't say does not exist for that. Finally, on the last one, I didn't even try graphing because everything was migrating. And so I get to use my handy dandy screen emulator here, TI emulator, and there's the graph of it. And so it's the same kind of graph. It's got vertical asymptote at x equals 3. Doesn't appear to have a removable discontinuity. Now I'm going to do a little something here. I'm going to hit zoom and hit zoom decimal on the calculator. And you can do this with your calculator as well. We'll do the same thing. And then the graph is going to look like this. Look at that. It wasn't there a moment ago, and now suddenly there's a space there. Got to have a little discussion. Sorry, this is going to be a little boring just listening to me talk about something, but normally we do this in class. So yeah, you need to know a little bit about how your calculator makes a graph. And what it does is it's got the x-min and the x-max. And on Zoom Standard, the window goes from -10 to 10. And then it figures out how wide each pixel width needs to be so that it can step that amount to get to the next pixel. Like, well, how wide should each one be so that when I get to the end of my screen, I'm at 10. And so it works out what that number is. Now on this one, on the CE version, it's 133 pixels wide. There's a little asterisk there if somebody's curious about it. That's not quite accurate, but I don't feel like talking about it. It's not that important. But you can treat it as 133 pixels wide. And so it needs to get from -10 to 10 in 132 steps because it's starting on the first one. So it does 132 steps and gets all the way from -10 to 10. And so you can realize when you look at the window, and that number there, that delta x is a little weird. It's not quite the right number, but actually the trace step is what you really want, is this 0.1515, that it's going to have to go by, it's going to have to step by a weird amount. Like it can't get from -10 to 10, go 20 units in 132 steps, all of them the same, and have those numbers be nice. And that's why whenever you trace your graph and you're moving around, that's why the numbers are so weird. You can see the 0.1515 there down at the bottom. That's how much it's stepping over every time, because it needed to step that much to get to the end of the screen at the right moment. At the end of the screen, I want to be at number 10. The interesting thing is the calculator then plugs in each one of these numbers and makes a dot, and then it just connects all the dots. And that's why it never notices that there's a hole at x equals 1, because it never plugs the number in. Like the calculator never plugged the number 1 into the function because it never had to, because of the pixel width. Right? Now, when I go zoom decimal, and you can see the graph, and there's the hole, the reason is it's adjusted the window now so that now you can see it's 13.2 units wide, that 133. If you're on a regular TI 84 Plus, it's actually 95 pixels wide. So it goes instead from -4.7 to 4.7. The CE has slightly better resolution. So you can see how you can see that now it's a nice number. And now look at trace step. Trace step is 0.1 on the nose. So now when I'm tracing, now it's going by exactly 0.1s. So zoom decimal adjusts the window size so that it'll be nice numbers as it steps from the one end to the other end for the number of pixels on your screen. So you don't need to memorize 95 or 133 or any of those things. You can just hit zoom decimal and it'll show you nice values. Okay? And that's why this time there is a hole, because this time it does plug the number 1 in. And so it goes, oh my goodness, there's a hole there. There's no value. And so this time it notices. The big takeaway on this is that you need to make sure to be thoughtful about your graphs, and don't just trust what you see on the calculator, because there may be something weird going on and you have to be a little more determined about it. Okay, so going back to the original, and the light's starting to go, so I'm going to turn my lights on here in a second. So there actually is a removable discontinuity. I could write it down below. There's a removable discontinuity. I know this is really bad, but I'm just putting it down here at x equals 1. There's a hole in the graph where 1 does not work in this function, and so there's a removable discontinuity. And now the limits, I kind of put this up in the air here. Now, if you asked about x equals 1, and looked at x equals 1, then the limits would be whatever you'd get. Let's see. Well, actually, I can try to think of the best way to do it. I could work out the limit, but it's a little tricky. So it looks like it's going to be for -1/4. No, -1/2. I'm doing that in my head. That's probably wrong. I'm looking. It's just before it's -1 on the nose. I'd have to look at that. It looks like the limit as x approaches 1 from the left is -1 and from the right is -1. And so overall the limit is -1. If you did instead the asymptote, of course you get no limit for the general limit, because it's approaching two different things. It's zooming off to infinity and different infinities. Okay, so that's the idea. Sorry that we had the technical issues there, and my Word document's having trouble too. And so that's basically what you need to know about limits at this point, about limits at infinite limits. Just you can answer infinity or negative infinity, but if it's a limit approaching from both directions, it has to approach the same way. It can't be like this. All right, so next up, we have limits at infinity. So consider this function. And the question is, what is the end behavior to the right of this function as you look to the right? And you can see it's getting closer and closer to 0. Right? And so this question is saying, what's the limit as x approaches infinity of f of x? Does this function get closer and closer in number? What is it? and it's 0. And so that's the limit. But I could see a student having an objection to this. This is one of those like read my mind teacher questions here. Like I could see a student raising a hand and say, well, hold on a second, and having a little bit of an issue about this. So we're having our technical glitches here again. So there we go. So did anyone guess what the student raising their hand is? Of course, I'm not going to call on you right now, but some students say, well, we've got an issue is that it approaches 0, but then it moves away from 0, and then it approaches 0, and then it moves away from 0 less, and then it approaches 0, and it moves away from 0 less. And so it's approaching 0, but then it goes away from 0, and it's going to keep doing that forever and ever and ever. It's going to keep having these smaller and smaller oscillations. And so is that a limit? Because it's 0 for a moment, and then it goes off, and then it's no longer 0. And so that doesn't seem like the limit's 0, because it's not, using our language, getting closer and closer to 0. Right? And so here's the explanation for why it actually is 0. And so I made a better window on this, just a longer one you can see. And so here's the actual definition of what a limit needs to be to have a limit. So you have to say, all right, suppose I made any neighborhood, and they actually use that word neighborhood, around the thing that I think is the limit. So I'm going to make a neighborhood of size 1 unit. And so my neighborhood around 0 is 1 unit. Then the limit at infinity is 0 if at some point in time, forever and ever and ever for the rest of the function, you're within that neighborhood. So, and you could see, okay, well, yeah, once I get, it looks like about x equals 10, it looks like. Once I get into 10, then I'm within that bound. I'm within that bound forever and ever and ever, and I'm never going outside of that bound. Now, that limit only works, though, if any neighborhood you make, and it has to have some width to it, and it has to be centered on what you think the limit is, any neighborhood you make, eventually you're going to be within that. So you'd say, well, what if I made my range around at 0.4 in each direction? So we go, okay, 0.4 and 0.4. What if we made it 0.4 around? Is there a time when, after that, forever and ever and ever, it stays within that range? And it's like, oh yeah, once we get to, we just went above there. It looks like after you get this. So clearly, I could even say x equals 30. Once you get past 30, you're going to be within 0.4. And no matter what neighborhood I make, so for any neighborhood, that does not want to erase. There we go. So for any neighborhood I make, is it eventually going to be there? Even if I made my neighborhood like 0.1, and I don't know if I made it on the screen here, it looks like I might just barely make it within there once I get x equals 120 or something crazy like that. And so that's what we mean by a limit, is that after a limit at infinity, after some point, everything inside is going to be contained within that. The same thing is true for other limits, like regular limits, is that if for any neighborhood around the y value that you think it is, at some point, all the function inside there is going to stay within that bound that you make, no matter how big or how small the bound is. Now, if we picked the wrong limit, like if we said the limit is 0.2 and we made a neighborhood of 1, well, yeah, then I made a neighborhood of 1 around 0.2, then, at a certain point in time, everything is inside that. But it has to be true for any possible neighborhood I'd make. And if I make a neighborhood of, 0.1 around this, then you can't say that eventually the entire function is going to be inside that neighborhood, because you can see it's outside of it there. So this is a real technicality, but it's just so people don't freak out when you see limits, when you see the closer and closer, and people start thinking about the closer and closer thing, and erasing, and they think, oh wait, does it have to be closer and closer? And so they freak out about some limit questions, like if they see something like the one we saw up above. Am I going to scroll? That function's having trouble today, or my computer's having a little trouble today. That they see one that's going that in those smaller and smaller oscillations. They worry about, oh wait, is that limit correct? And so the answer is, yeah, that limit is correct. It's okay to move away as long as it's staying closer and closer and closer and closer eventually. Okay. Now we're going to talk about limits at infinity next. and how you'd know these things without a calculator. And it's going to be a little bit of review for next year, but I think I'll pause here so that the video isn't too long. Thanks.